Welcome to Land Eco Lightning Talks and Thinking Like a Landscape with Dr. Kevin McGarrigle. In this 8-part series on the natural range of variability concept and current departure, I discuss the origins of the concept, definitions and alternatives, applications, and important considerations in the implementation of the concept. In this talk, part 6 of the series, I'll talk about the importance of place and time. Okay, let's get started. Recall from a previous talk in this series that the implementation of NRV is fraught with some major challenges and some very important decision points. Probably the most important challenge and decision is with regards to the choice of a reference framework approach. And we talked about 4 major approaches. We talked about the historical range of variability approach. We talked about an aspatial version of that. And we talked about 2 space for time substitution approaches, the contemporary reference condition approach and the historical reference condition approach. Without doubt, the choice among these reference frameworks is the biggest challenge and certainly the most important decision to be made when implementing NRV. In the subsequent talk, we talked about the scale dependency of NRV estimates, regardless of choice of reference framework, and how important it is to be careful and explicit in the choice of both spatial and temporal scales when assessing NRV. In this talk, we want to talk about the sensitivity of NRV estimates to the spatial and temporal context of the assessment, that is, the place and time of the assessment. And this idea, just like the scale dependency, stems from the second and third axioms of landscape ecology that I discussed in the first series on the landscape concept. Axiom number 2 is that landscape pattern and process is scale dependent, and axiom number 3 is that ecological systems and landscapes are spatially and temporally dynamic. Let's begin by looking at the historical range of variability reference framework approach and think about the variation or the sensitivity of HRV estimates to location and time. In this particular example, we have a landscape classified based on vegetation developmental stage, so essentially from open canopy through tall tree stages. And although it's not shown here, envision a chronological sequence or a series of landscape snapshots over time depicting changes in the developmental stage mosaic. And depict and also consider varying locations within this landscape that we might be interested in assessing HRV. So we might ask the question, what happens to HRV estimates if we change the spatial context, that is the place, while holding the spatial scale constant, the extent of the unit, and controlling for biophysical setting? And by biophysical setting, I mean essentially the underlying terrain, soils, and climate conditions and vegetation types that vary across this landscape. And if we try to control for biophysical setting, so for example, by choosing locations that are similar in their biophysical setting, so they have similar terrain characteristics, similar soil conditions, similar climate conditions, and similar vegetation types, and more specifically in this particular example, thinking about sites that would have a similar level of forest productivity, okay? So if we choose sites that are very similar in their overall forest productivity as driven by these biophysical underlying conditions, and look at how does the HRV estimates on these relatively similar sites vary from place to place, and we're holding the spatial extent or spatial scale constant. And here's what we find. On the left, we're looking at the contagion metric, a measure of overall vegetation clumpiness in the developmental stage mosaic. And we're doing this for the biophysical class that represents kind of low productivity sites. And we've just chosen 3 random locations on low productivity biophysical settings and computed the historical range of variability in the contagion metric. And what you can see clearly is that the 3 sites have very different ranges of variation. Not only is the range itself broader in one site and in one site versus another, but the absolute ranges, the actual contagion values, varies from site to site. So essentially depicting the fact that each site is unique in its HRV and contagion. On the right, if we look at all of the sample sites, and I believe there were 1,000 sites within this broader landscape, and for each of those sites, we calculated their HRV and contagion and depict those as a box and whisker plot, although it's hard to see the boxes at this scale. What you see here is that across the 1,000 locations in this landscape, that the HRV and contagion varies dramatically across sites. No two sites are exactly the same. While some sites may have relatively similar ranges of variation, they're all actually unique when you get right down to it. And some of them are actually quite different, as you can see. Importantly, as we change the landscape pattern metric, so instead of contagion, if we look at other metrics that deal with both landscape composition and landscape configuration, we observe very similar HRV sensitivity to spatial context. That is, location matters. Each location has a unique range of variability in each of the metrics of landscape pattern. Although the exact nature and the magnitude of context dependency is unique for each metric. In other words, we don't see the exact same patterns for every metric across sites, but we see the same general finding that there is great sensitivity to place or to spatial context. And that's depicted in this example, which was presented in some of the previous talks for a landscape in northern Arizona, centered around the San Francisco peaks and Flagstaff, the town of Flagstaff, just south of the Grand Canyon. And we have three nested landscapes here, the peaks, the San Fran, and the Sunset. In the last talk, we talked about the scale dependency and showed or talked about how the range of variation over time varied as one changed the spatial extent. So as one went from the peaks scale, the largest scale, down to the sunset, the finest scale, the range of variation, the variability over time increased. But what we want to talk about here in terms of how and why place matters, landscape context matters, that's depicted by the vertical relief or the vertical differences in these three trajectories. So the peaks district, the largest scale landscape, has a range in this metric, the aggregation index, that is relatively low. It's around 78, 79. And the San Fran landscape depicted by the red dashed line in the middle, not only does it have a slightly higher range of variation, the scale dependency, but also its absolute range is greater. It ranges around 83 to 84 for this metric. And as we go to the sunset landscape, the smallest landscape, not only is the variability greater, this scale dependency we already talked about, but you can see the range of values is now even greater. It's on the order of 87 to 88 or 89. This difference in the absolute ranges is due to underlying geophysical or biophysical differences in the locations of these three landscapes. The sunset landscape is sort of unique in that it's a relatively homogeneous ponderosa pine forest, but punctuated or subdivided by some rather unique geological features owing to some fairly recent geological activity. The San Fran landscape has a variety of vegetation types owing to the pronounced elevational gradient because it's centered on the landform of the San Francisco peaks. And then the peaks area, which encompasses both of those two features, it incorporates some other geophysical settings depicted by the red in the legend here that brings in essentially a whole different biophysical setting that is simply not present in the other two landscapes. The important point here is that each of these three landscapes, forgetting the difference in size, are just fundamentally different places. They each have a unique context in terms of the geophysical setting within the landscape, and they each have a unique context in terms of where they are situated geographically in relationship to other geophysical settings. And that is what produces the different range in the metric in the example shown here for the aggregation index. So this difference is simply due to unique landscape context. Why does this happen? Well, because each location has a unique biophysical setting and it has a unique spatial context. That is, it's situated in a unique place within the broader landscape. No two places are the same. Every place has its own kind of idiosyncrasies that arise from kind of the uniqueness of its underlying biophysical and geophysical setting and its unique position in the broader landscape. And that unique setting or context affects pattern and process. So as we look at some of the major drivers of disturbance in vegetation, a few of the examples shown here, we see that there's just no two places that end up being the same. And this has important implications. If we look at the contagion metric again across those 1,000 sites that are distributed, geographically across this broader landscape, we see that for any one site, there's a relatively narrow range of variation, and the absolute range varies from site to site. If we were to compare the range of variation for one of those sites to the range of variation across all of those sites, which is what happens in a space for time substitution approach, then what happens is place becomes confounded with scale. Because at any one place, we would expect to see a range of variation that's unique to that site. And as we compare that to the range of variation across many sites, we're essentially increasing the range in this case that we might expect to see across multiple sites. So we essentially confound place with scale when we do that, making the interpretation challenging. So just like the sensitivity to place, we also have sensitivity to time. That is, the HRV can vary with the reference period. And that's shown with this example here from British Columbia. Again, an example that was presented in the previous talk, where we have on the y-axis kind of an index of tree species composition that ranges from species prevalent during wet, cool periods to species prevalent during warm, dry periods. And if we look at the changes over time, we see that each period in time is somewhat unique, owing to the unique climate of that period that favors one vegetative community type over another. And you can see here I've depicted 5 different periods in time, each of which would have their own HRV, because each period in time, just like each place, is unique or idiosyncratic. So why does this happen? Well, again, we've talked about this before, but because of climate variability, which largely drives disturbance regime. And climate variability varies over time due to long-term climate cycles. So not surprisingly, if our reference period conforms to the Little Ice Age, we're going to see something very different in terms of an HRV than if our reference period conformed to the medieval warm period. So the period in time, as well as the extent in time, can have a big influence on the HRV. So comparing the HRV of any particular reference period to a different period can be problematic, right? Because each landscape is kind of unique in time. The expressed variability over time is unique for a particular reference period. And thus the time period becomes confounded with scale. And by that, I mean the choice of time period and its extent is specific for the measured HRV. If you change the time period or if you change the extent of that period, the HRV is going to vary accordingly. So the time period and the time extent ends up being coupled with the scale, the temporal scale of the assessment. And the NRV, or HRV in this case, is specific to that explicit time period and extent. This idea is tricky for NRV approaches that use space for time substitution, such as the CRC and HRC approaches, because in these approaches, the reference period is actually undefined, right? There is really no temporal dimension to those approaches. So it's difficult to think about the time dependence of the NRV estimates in these space for time substitution approaches. So let's finish by quickly talking about considerations of place and time for each of the four major NRV reference frameworks, beginning with the contemporary reference condition or CRC approach. In this case, we're comparing one place to several other places, and thus there is a confounding of NRV with place-based idiosyncrasies. Now, that is because each place is unique or idiosyncratic in its underlying historical range of variability and is unique because of its underlying unique biophysical setting and landscape context. When we compare any one site to a range of other sites, we're in some ways comparing apples to oranges, right? Because we're comparing a site that is truly unique to sites that are unique in their own right. Secondly, the time period represented by space for time substitution is undefined, right? And thus it's ambiguous. It's hard to couple the NRV estimate to a time period or an extent of time because time is not explicit in these approaches. And these two things really represent the major shortcomings of this approach. Most importantly, the confounding of the NRV estimates with place-based idiosyncrasies. And essentially the agnostic nature, the fact that it's agnostic to time makes it difficult to assign a time frame to the NRV estimates. The historical reference condition or HRC approach essentially has the same considerations because once again, it is effectively the same approach. The only difference being instead of the contemporary landscape, we're taking a single historical snapshot of the landscape, but otherwise the same considerations apply to this approach as well. The historical range of variability or HRV approach accounts for the uniqueness of each place by comparing it to itself. So there's no confounding of place-based idiosyncrasies. This is perhaps one of the major strengths of this approach in comparison to the others. It also accounts for the uniqueness of the historical reference period by making it explicit in the simulation modeling. And really, these two things combined really represent the major strengths of this approach. The aspatial historical range of variability approach, as we've talked about before, spatial scale is not explicit, and thus it's ambiguous. Temporal scale is not explicit, thus it's ambiguous. And of course, because neither space or time is explicit, multi-scale approaches are not feasible with this approach. Well, the major take-home message for today is that NRV is extremely place and time dependent. So be cautious about comparing NRV results across spatial units that differ in landscape context, a problem that is effectively unavoidable in the space for time substitution approaches and is dealt with in the HRV approaches by controlling for landscape place because each place is compared to itself over time. Second, be cautious about extrapolating NRV results from one landscape to another because of the uniqueness of place or landscape idiosyncrasies, or from one reference period to another because of the uniqueness of time. The best solution, of course, in my opinion, is an HRV for each place because this avoids the place-based problems associated with place-based idiosyncrasies and makes the temporal period explicit in the HRV approach. Well, this is Dr. Kevin McGarrigle signing off from this episode of Land Eco Lightning Talks. I hope this talk has been helpful, and I hope you join me for my next lightning talk. In the meantime, keep on thinking like a landscape.